testing standby power of a USB mains adapter, in particular this Amazon mains adapter here. We're going to be using it offload and determining how much power it uses in standby mode. So the equipment being used is the single phase breakout box. This is a Newton's 4th designed box. Provides easy access to the voltage and the current for the power analyzer, and it also offers a universal breakout plug for a range of devices. In this case we are using the UK mains designed mains adapter. So the power analyzer in use is the PPA 1500. Today we have a 3-phase version, but we are using it in single phase mode. We're only going to be measuring single phase power. Of course, if you are using this in a production environment or a test house environment, then what you can do is use every channel, testing 3 devices at a time. So providing 3 independent measurements without a problem. So with the instrument turned off, what we're going to do is run through the entire setup sequence in order to measure standby power. And this is in accordance with EN 50564, or the old version, which is IEC 62301. We have software available that automates the test, but this is the manual setup of the instrument in order to measure standby power. So let's turn the instrument on. You'll notice very quick boot up time. This is a custom operating system developed by ourselves. So what we have here is phase 1 being displayed, but as this is a 3-phase analyzer and I'm only using a single phase today, I'm going to turn off the second and third phases and use single phase 1. So that's just using the first phase of the instrument, which is what we're connected to on the rear of the instrument. So after making that setting, we can just have a quick look before we go into anything else in the application menu. Now in the application menu there is actually a standby power mode to enter. Now what this does is it extends the averaging slightly and enables the instrument to synchronize its window upon the current waveform, and that's very important, especially when the current pulses are not synchronous with the voltage cycle, with the 50 Hertz. So we've got 50 Hertz mains here, we've got a current of 1.2 milliamps. Now this is a 20 amp RMS unit with all of the PPA 1500s. What we have is the option to change the ranging system from a 20 amp to divide by 10 to a 2 amp ranging system, 2 amp RMS, which divides the bottom range of 100 milliamps by 10. So if we put internal times 10 there, the bottom range becomes 10 milliamps, and that's much more suitable for a 1.2 milliamp signal here. So if I've just changed that now, we can see that we're now on the 30 milliamp range. The reason for that is going to be the crest factor. So if we just look in the RMS menu here, let's have a look at the crest factor. So the crest factor on the current here is 8, 7.5, bouncing around. That's a huge crest factor, and with other USB adapters you can expect crest factors of 12, 13, somewhere around there. So it's important when choosing an analyzer to ensure that the manufacturer guarantees accuracy upon high crest factors. It's common to only specify accuracies up to a crest factor of 6, for example. So what we're going to expect when we look in the scope is quite a peaky current waveform and a sinusoidal voltage. Now the crest factor is 1.39, that's because it's a flat top UK mains voltage. Of course in a test environment you would be using this with a sinusoidal AC source, and in another test later on in the tutorial series we're going to be using the Newton's 4th N4A 03 3 kVA AC power source, which is very pure sinusoidal waveform, perfect for a test environment, standards compliance. Now here we go, here we can see it's a very low RMS and a very peaky current Here's the UK mains voltage. Just change that. The trigger is on current. So we can change that trigger down and we can get a nice steady scope trace. So you can also screen print this if you wish straight to USB. So let's go back into the power mode. There's not much else to do now with the configuration. The instrument is ready to perform the measurement and it will be very stable. We can see 105 milliwatts here, very stable result, even on that very peaky, really fluctuating current signal. 1.7 milliamps, 244 volts, and 106 milliwatts there, very steady. If we want to look at quickly the harmonics, we can have a look in the harmonic menu. It will show us the distortion on the voltage and the current. And if we can look at it in graph, we can see huge distortion on the current. It's very peaky, non-sinusoidal. So that was standby power measurement of a USB adapter, very low power, with no problem with the internal shunt. Now if powers go even lower than this, what we can do is use an external shunt from the N4L range. A HF003 for example is a 3 amp RMS shunt, and that would provide excellent measurements down to microamps.